Our next speaker is Ken Witherly. He's going to be talking on, the title of his talk is Geophysical Signatures of Carlin Systems formed along the northern margin of ancient North America. Ken graduated from UBC, University of British Columbia, Vancouver, Canada, with a BSc in Geophysics and Physics in 1971. He spent 27 years with the Utah BHP Minerals companies, during which time, as chief geophysicist, he championed BHP's progress in airborne geophysics, which resulted in the development of the megaten and quantum technologies. And in 1999, Ken helped form a technology-focused service company that specializes in the application of innovative processing and data analysis to help drive the discovery of new mineral deposits.
Thanks, Bob. Those that you know me know I wear a number of hats. The first announcement is we're having a SEG Mining Committee meeting tomorrow at 7:30 in Dixie Restaurant. The 24-hour joint downstairs anyway, so whoever wants to show up, I've got 12 copies of the minutes from the March meeting, so bring those along. So tomorrow, 7:30. Not too early, Brendan, not too late. To my talk and the handout, there's more material in the handout than I have time to present. I kind of dithered about that a bit, and I figured, okay, there's probably some value in putting a few more examples into the book, and the organizers didn't complain, so you're going to see a subset here to shoehorn into the 25 minutes they've given me for the talk. This is still a work in progress, and I thank John Legault for introducing the slide here and a couple of others, and I knew he went down to the genome level on ZTEM, so I don't have to have any slides to this. Few people know that John was actually born the year that AFMAG was invented. He actually has a cosmological link to the subject. It's really awesome. Not many have that. One of the things in comparisons, and we've done a fair bit of this in my company, is we generally try and start with a place you know a lot about, say with a new technique, and then you go to a place you know less about, and say justify using that technique and try and learn from that. The odd thing is when I looked at the presentation and the title, even though the Carlin is the mother lode and has been known, I think, since the 60s, looking at the geophysical signatures, particularly for things like ZTEM or some of the active source EM systems, there isn't really a lot of information that's out in the public domain that you can access. So trying to build a case as to what these signatures are like is a little bit iffy. But we actually had the chance to go to call it a Carlin wannabe or Carlin-esque situation up in the Yukon. And we have a pretty good AFMAG ZTEM data set up there that is going to really be more of what we have as a solid case history. Down here in Nevada, we're still trying to build the case. We have some information that's in the book from Carlin Gold on their Cortez Hills project, and it's certainly in the interesting area, but you can't call it a Carlin deposit. They're still in the proving up. They've got the right stratigraphy that they feel, but we don't have an ore body. They are just a few kilometers away from Gold Rush, and rumor is there may be a data set over Gold Rush, but that's business that we can't discuss here. So it's going to be a kind of an odd case history, because really it's going to be the student teaching the teacher here rather than in terms of examples, but if you can follow with me. So it's great. Rodinia, 700 million years ago, things started to break off, and one of the things that struck me just in the last year or so, listening to a lot of the discussions about undercover exploration and how you define prospectivity, it seems almost everything of real interest occurs at some sort of crack in the earth. Some place where something was either coming apart or coming together over time. And it doesn't matter. If you go into the Yilgarn, most of the nickel and gold deposits are all formed, they feel, along fundamental structures from the Archean. And now it's all sealed up and it's all called the craton. But you look at it in a fundamental crustal sense, And there was, I won't say bad things, but very traumatic things were happening when those deposits were formed. And so we have a similarity here, I think, breaking off of these slabs for, actually Australia was heading north, I guess. Geez, I didn't realize the Yukon had that affinity. But anyways, there you go. That's what the argument is. Nowadays, of course, they look like that. It's about a 3.5 hour flight for people from Whitehorse who want to come down to Reno. You know, okay, not so bad. I'm not sure many people going from Reno going the other direction. At the edge of the continent, a lot has happened in Nevada. Clearly, that's one of the things that when you read the literature, there's been far more traumatic history going on along the edge. Let's see if I get that. Along in through here, it's almost like an accordion to me. For 700 million years, it's been coming together, going apart, going up, going down. Intrusions have come up, they've been eroded. So there's been an enormous amount of preparatory work. And then, of course, as we saw even this morning, there's a series of these super plumes that have moved across, currently sitting up in Yellowstone, which is very interesting for a resident of Denver. But anyways, a lot of preparation. And there was some slides that I presented at the meeting 2 years ago. I have a few of them here, but it's very, very impressive because I think things happened here that probably haven't happened nearly to the same degree in the Yukon. And that's probably one of the reasons why we don't have all the trends in the Yukon. Right now we seem to have one where we have Carlin-style mineralization. Anyways, I'll flip through these, showing the location in the Yukon. I'm actually just north of where Jean was talking about. That ZTEM survey sits in here. The ATAC and Rob Cairn, who was as Jean indicated, the lead author in his talk, his company is focused on this Rackla trend up in here. They've tagged this probably about 7 years ago, and then they found at the eastern end of it, it was starting to look like a Carlin system. Though you go into the middle of it, it looks much more epithermal. And you go to the west end of it, and it's almost becoming a VMS style terrain. Anyways, different story. So that's the background setting here. We have a onshore or main cratonic mass here, and then we have sediments that have come in over time, but really not, and I'm not trying to simplify it horribly, but not nearly as complex a story as we have in Nevada. Here's some of the cartoons that Jackson put together. He actually has an oral piece that goes with it, and for me, who didn't know that much about it until a couple of years ago when I put the first paper together about this, very, very interesting. You know, mantle underneath here, basically off to the right, your mother lode or your very old rocks, and then starting this process of back and forth, transition sediments, limestones. Roberts Mountain, partial melting. And this is spanning this, 500 million years of time, because really the gold events were very, very late, very, very recent. Although they seem a bit older in the Yukon. The Christmas tree, I like the Christmas tree because I think I'll show you in a bit. I think we can see maybe a Christmas tree style mineralization because this old structure. And that's one of the things that Karen did say when he looked at the ZTEM results. He says, our structures in the Yukon have not really, they're more just cracks. They are not really things that have had a long history of movement. And so that probably has some control on the extent and the size of the ore bodies that are found. The grades are very good up there, because you've got to have really good grades in the Yukon. But when you look at the location of mineralization, it tends to be fairly localized, and probably hundreds of thousands of tons, and then another 100 meters, and another 100,000s of tons. It's they seem to be quite a bit smaller than the feel I get for the systems here in Nevada. So, final breakup and formation. I know the geologists all know this. Expiration points. Some of the examples I have in the book, and I'll show you from Nevada. These aren't Carlin style because the data doesn't exist, or if it does, I can't access it. What I'm trying to show is we can map structures very effectively to things like the AFMAG that are very complementary to magnetics and gravity if we have them. So I've picked a few things that are out in southern Nevada that I think have at least geophysical analogies that we can use. Here's a little more detail on where the Rackla trend sitting in here. Here's the Selwyn Basin, big sedimentary pile. These are sedimentary rocks as well. Underlying it, of course, are more mafic rocks, Proterozoic, Neoproterozoic rocks. John showed this section here. You can see the Dawson Fault, and I think there's thrusting along this, I think would be, if you've thought about it, John, the equivalent of the Roberts Mountain. If you were going to say, where's the big structure in the Yukon that's analogous to the Roberts Mountain, I think the Dawson probably is going to be it. And here's it's just this cartoon. They show the location of the known gold mineralization sitting in here. This is where the base metals are. That's a VMS deposit called the Margin here. And then the stuff that Jean had would be further off to the left in the more SEDEX environment. Now, one of the things that I think Jean spoke the words, but you have to look at a picture. This is really, really rugged terrain up in the Yukon. This is very, very challenging. So when you look at a plan map, think of it as all being stuff like this, 3,000 to 4,000 feet high cliffs. And here's the Dawson Fault along here, and the mineralization is basically sitting in this package in here. So it's a fairly narrow strip, 10 kilometer scale bar through here. The three deposits I'm going to look at, that was sort of the geology preview. In the book, I've got some from the Cortez Summit, which I showed 2 years ago, and I figured didn't require to repeat myself. I would certainly encourage you to go to Carlin Deposits' website to get updates. I have examples in the book from Freeburg and Witherly. We did the work on this a couple of years ago. They published it, not as a 43-101, but they just loaded up our reports onto the website, so that's where that data came from. And I've got slides from one of these. I'll show you just a few. Geology, here's, this is from the Witherly deposit, more of an epithermal style system, sediments, volcanics, basin and range faulting. Here's basically a summary geology image. We have altered tuffs, sediments in here, younger volcanics across here. And so we're seeing some of the story with the magnetics, and that's always good, because mag is your friend, as trends are your friend. We have some regional gravity. There seems to be a big high-density spine sitting through here. This is the sort of thing you say, well, that's to be expected, but it's a very difficult thing to actually target anything on with that sort of resolution. Maybe with higher density it might be more interesting, but this is typically what I have available. This is the 90 hertz total phase rotated data. And here we're starting to see much more, I would call it, coherent structural impressions coming out of the AFMAG data, of the ZTEM data. And here we have the showings, and here you can see they're wrapped around a more resistive area in here, and a fairly major. This can either be a fault contact between rocks of two resistivities, or there can be a conductive component actually in it itself. It's somewhat ambiguous, because it's current channeling, so it responds to changes. Those changes, depending on the ratio of the two resistivities, control the amplitude. There also can be conductive things at that fault, but those are two different things which often, in the case of interpreting these sorts of data, you have to keep your options open. So this is the sort of results here. We have probably some fairly thick material, valley sediments off the range front. And as Jean said, the AFMAG is very good in terms of depth of investigation. If you ran, like years ago, there was it seemed like the Digim and the Aerodat systems were very popular in Nevada, and there was a whole wave of surveys sort of through the late 80s, early 90s. And those things we're only going to be seeing down 60 to 70 meters. Whereas with the ZTEM, you're seeing down 500, 600, 700 meters, depending on the resistivity structure. So you're getting a look that's more than an order of magnitude better with the new technology. So that's the Nevada stuff I was going to show. Focus now, because I have real data. I have real ZTEM data over the stuff in the Yukon. And you can see here on the scale bar, 5 kilometers, here's the Dawson thrust. And here are these series of now, they haven't actually put a PEA out or a 43-101. It's one of those cagey things right now that they're reasonably well funded. They've got money in the bank. Agnico Eagle is supporting them. But they really don't want to rush to an economic assessment, because I think they feel the market is going to probably be fairly harsh to them because they're in a very remote part of the Yukon. So they drill and they get some great results, but you know, I've seen people with things that are 25% less the quality of this, and they've rushed out, you know, to the market to try and raise large amounts of money. ATAC is being very conservative about it, but certainly you can see here, again, the 5-kilometer scale. There's sort of a 10-kilometer distance between these two nodes. Within these, you know, you're getting these zones of mineralization. They've done, I think, the breakdown based on the original geochemical grid, but geologically, I'd have to think, you know, you draw a pit outline around this, and you draw a pit outline around this, and there doesn't seem to be much in between. Geochemistry has been very, very important for their assessment here. And then once you move north of this structure, the Kathleen Lakes Fault, you're basically back into continental sediments. And so the kill zone for the mineralization is really between the Dawson and the Kathleen. This structure, you got about 15 kilometers. So it's like the Carlin trend, but there's only one. That's at least what they've found so far. And I'm sure they've been, and in terms of other competitors, well, most companies never say they have a competitor, but Anthill, a Chinese company, sitting off the east end, and they seem to have the last piece of this particular piece of stratigraphy. And they're struggling to figure out what to do with their little bit, but I think they seem to have similar mineralization to what Archer Cathode has here at ATAC. Here's a section. This is useful, I think, from the point of view of, it shows the grades. You can see some, 4+. You got some 9 grams material in here, 5, 6. So some very nice grades, but it's interesting. You can see there's this developed zone here, maybe a weathering effect, because a large part of this part of the Yukon wasn't glaciated. And then there's this barren zone. And then to me, this kind of, I drew a little cartoon, I didn't include it, but sort of showed a Christmas tree. The way these intersections are, they're not really all that consistent, but where you get them, they're pretty good. I mean, having 25 meters of 3 grams is nothing to shirk, but then you've got a lot of waste rock in between. So I think it's going to be a difficult proposition from the mining perspective. This is the Conrad, which is one of the eastern zones. They have identified some other stuff here. I think they've done a 43-101 on what they call the Tagger Zone, which is about 100 kilometers to the west, and it's more of an epithermal association rather than what they're calling their Conrad style. Now, one of the interesting things, of course, we should be a data-driven business, and Chet did a wonderful introduction to tilt. I got lost when you talked about the cosine part. There was a sine. Anyways, this is an environment where there are no volcanic rocks. These are all sediments: limestones, siltstones, cherts. So where in Bejabbers is all this freaking mag coming from, right? It's amazing. This was flown with the Z10 system. It's not the best mag in the world. It's extremely rugged. They fly high, 200-meter line spacing, and yet we're seeing detail. This mapping was done, it was a special project by the Yukon Geological Survey. They put out their entire 8-person team to map this entire area in as much detail as they could. An outcrop coming out the wazoo. And they couldn't see everything. Now, my recommendation after we saw this, here's the zones in here, the Conrad sitting in there. You can just see, okay. So you have a lot of character. What does this mean? You know, it really, until you start translating it into geology and then trying to use it in a predictive way, it's just images. It doesn't mean very much. Well, unfortunately, all of the work we did was done 2 years ago. And once what happened to gold happened to gold, ATAC basically went into their shell and said, we only can drill geochem anomalies we currently have. All of the geophysics stock, all of the assessment, all of these data sets have just been put on hold, which is great because it means at some point somebody will crack it open and look at it again. But it was quite frustrating for us because we saw that we had a lot of information in these data sets that potentially could help at least, maybe not target drill holes at the scale this data does, but at least characterize the setting that this mineralization is hosted in a way which would be, because we have a block of data here at the far east end, and then there's about 100 kilometers where there's nothing. There's only like 2-mile spaced mag data from the GSC from the 60s. And then at the Tagger zone, the data density starts to pick up again. So there's a large part of the trend here that really hasn't been had much justice done to it. So anyways, I'll stop whinging. Here's some of the images. I'm going to wander over here so I can read them all. So we've got in the upper left, Z10 180 hertz. This is the Conrad zone in there. You can tell by the pink dots that's the density of the drilling or where the ore shells are. So you can see this structure here in the Z10, this embayment. You know, that's kind of cool. It's sort of like we're just really at trendology here. This is not hard and fast interpretation. We looked at the drill hole information. We put the mapping of the Yukon Geological Survey on here, and we dropped them onto the various products, some of which came from Geotech directly, and the 3D ones which we generated. There's a geology map down in here. This is a depth slice in the conductivity model. Looks a little bit different than the 180 hertz, which would tend to be a little bit shallower. We see this very strong embayment over here, and this really seemed to be cupped in this just like this, and that's where the mineralization is. Mag, sitting down in here, we're mapping one of these thrusts very, very closely. I call it a magnetic wall. There's the thrust contact right through there. It seems to be broken by these two north-south ones, which is interesting because we don't get a lot of geophysical support, at least in the mag, for north-south features. And they have a couple of real rippers that go through here. And that was one of the things that ATAC questioned. They said, well, maybe because there's a lot of, even though it's very rugged, there's also valleys and places where you can't really get down and map particularly well. That some of it might have just been, they saw something here and they saw something over here, and the natural tendency is just to connect the dots, right? That's what you have to do if you can't get access to it. Here's a little zoom in on the 180 hertz. You can see the mag is shown up here as contours, and you can see a bit of see that line there in the contours. The mag and the Z-TEM are really kind of showing some sympathetic character as they are up in here, but not everywhere. And you see the mag is showing some character up in here, and across through here there's not really as much on the Z-TEM per se. So it's really a combination of the two, I think, are going to be the strong suit. And this is about the only thing you can do. I mean, it's impossible to do IP. It's all rock, or tailless, which is you can't get any electrodes into. It's got permafrost, and the relief is such that, you would basically kill people if you tried to do ground geophysical surveys, I think. It's a very challenging environment in that sense. Zoom in on the tilt, some of these structures, to say we saw some patterns here. This slight embayment in the mag, which shows up in the Z-TEM as well, and yet we're not seeing anything. We're seeing that one with the geology. They seem to pick up one piece, and then nothing through here. So we could certainly think that we could probably enhance the structural map very, very well if we sat down and put our feet to the coals. But unfortunately, the clients have other things to focus on. I'll finish off on a few 3D models. There again is the main eastern zone. This is looking down on top of a conductivity model from the Z-TEM 3D, and here's a section through here. So the drilling, it's all focused in here, and there's that embayment that we saw there. And you say, well, could you target on something like that if you didn't have the geochemistry, the arsenic geochemistry, and the realgar and things like that? No, I don't think that would be unique. But once you move into the environment, you're starting to see things that actually are part of the neighborhood. The client found the house, but he doesn't really understand the neighborhood very well. I think that's where this geophysics will assist. There's the mag. There's what I call the mag wall. That's on the north side. And I say, I won't overly emphasize the point, but this is basically all a sedimentary package. So these must be very, very low level amounts of magnetite sitting in these sediments, which are not mapped. There's nobody doing susceptibility. So we're out there imaging stuff that, as far as the geologists are concerned, doesn't exist in time and space. It's wonderful. Just wonderful. Anyways, physical properties are critical. I haven't heard too many mention that today. Some people will push that story much harder than I will, but it would help. Snapshot of the 3D mag and EM over the Conrad zone. Sitting in here, there's the mag wall through here. Now, one of the things about these 3D inversions, you know, beware of things at depth. Greg Shore talked a bit about, you know, kind of like the land where the elves and the hobbits live, and you have to be careful when you start to get too deep. But I'd be pretty confident about the upper 500 meters. I think that's probably pretty robust. Things a kilometer or more, take with a grain of salt. So, I wish to thank Bob, who's in this room, Bob Thomas of Carlin Gold. I didn't show too much of his stuff today, but it got us kicked off a couple of years ago. And of course, Rob Kieran at ATAC and David Monahan at the Yukon Geological Survey. Thank you.
Thank you, Ken. Right on time, and we have time for questions.
Brandon.
Has anyone thought about flying to Reno yet?
Magnetic, he's talking.
Gravity. If you draw conclusions to the data, gravity first class. Was there any talk about that attack, or
the GSC, because the Yukon is a territory, the GSC basically is their big brother when it comes to geoscience. And I think there may have been some discussion about, something like the Sander air graph. But radiometry, I think, would be challenging for the terrain corrections and nothing else. There is a bit of gravity further west over the Tiger Zone, and it kind of looks like the terrain is not so evil there, and they've done ground gravity, and it looks interesting. But there is a fair bit of regolith here that kind of adds complexity to the near surface interpretation. It also makes for some of the mineralization to be more amenable for milling and stuff like that, but it's not a huge thickness.
Okay. Thank you, Ken.
Get my book.